In this section, we're going to take a look at a general approach to hypothesis testing, where we have many different scenarios that we have to sift through and decide what are the best methods to use in varying circumstances. So now at this point, we've examined the theory and the logic behind our hypothesis testing. Let's take a look at the step-by-step strategy that we have in actually doing these tests. When they're not sectioned off by section, how do we know which is the best approach? The first thing, and we did a very similar thing with confidence intervals, but the first question we have to ask is, what is the parameter that's being measured? Remember, a parameter is a number that describes a population. So in a confidence interval setting, we looked at means and we looked at proportions. So a mean, of course, is an average of a population, and a proportion, P, is a percentage. So is it a population mean? Are we trying to measure a population mean or a population proportion, P? Remember that depending on that answer, we have different formulas for each of those parameters. As you're preparing and keeping yourself organized, getting ready for the tests, I highly recommend that you put on a note card the formulas for when we're dealing with population means and formulas for when we are dealing with population percentages or proportions, because you don't want to get them confused. So, depending on your answer to that question, if it is a mean that we're measuring, we have to ask a second question: do I know the population standard deviation, sigma? This is ultimately the part that our next decision, whether we're going to use Z or T, hinges on. It's not about the sample size we have. It's not about whether we took a random sample. In fact, we're assuming a couple of things in most of our tests. Number one, that we had a decent random sample that was taken. Two, that the underlying population has a normal distribution. If those two things are met, we can use both the Z or the T curve, depending on this last question, which is, do I know the population standard deviation? Generally, if you're being given a standard deviation, most of the time it's from a sample. But once in a while, they will say, assume the population standard deviation is such and such. Or they may use the symbol sigma. When that's the case, you know that you can use Z. If we know sigma, we can use Z. Remember, sigma and mu are the important parts of the standard normal curve. And that's what Z is. The problem happens when we're not given a population standard deviation. When that's the case, we need a standard deviation, and so we look to our sample to estimate that. And of course, when the source of my data is a sample data, we use S rather than sigma as our estimate of sigma. So think about this. We don't know what the population standard deviation is, so we're using kind of a fill-in number to estimate it. And whenever that's the case, that's when we have to use the T distribution, as it'll give us more error in our calculations. In the T curve, our tails are a lot thicker, and so we have a little more error in our estimations of the population parameter. If we have a portion, then we're going to use the Z curve. And depending on the book you're using, sometimes it's n times P has to be greater than 5, or n times its complement has to be greater than 5, but other times it's 10. I think most books actually use 10 at this point. But regardless, this will always be the case for our problems that we're using. Once we've done this, then we're going to do our testing. The critical value approach is another one that I have in another video linked in here. This particular lecture is simply going to focus on the p-value approach, which is what we're doing for this video. as we test our hypotheses using a p-value approach, we're using it from a probability approach. And it's probably the more common way that in the real world hypothesis tests are carried forth. The reason why is because probability offers us a look at our sample result without necessarily having to draw a line in the sand. For our purposes, we do draw a line in the sand. We're going to establish a significance level, and our p-value has to be less than that significance level. But a lot of times in real-world situations, our p-value actually tells us the strength of the evidence against the null. The lower my p-value, as we've seen, the stronger the evidence is against the null hypothesis. So, in approaching it, we first have to state our null and alternative hypotheses. What we're going to look for in the wording is what does the researcher believe, or what is being stated that they want you to test for. That should be what you put in the alternative hypothesis. The alternative is usually testing some sort of assumption about the population, which is where we put the null. The null should always be in equals, and the alternative will always be less than, greater than, or not equal to. And it's depending not on the outcome of this test statistic, but rather on the wording of the question. Okay? What is the assumption or belief of the researcher? That should drive your alternative hypothesis direction. The null, we can always say equals, and we're looking for that number that is in dispute, right? That's the thing we're trying to challenge. So the null and alternative hypothesis are arguing about the same number. The null says it's equal to some number, and the alternative says that it's less than, greater than, or simply just not equal to. So once we have determined our null and alternative hypothesis, then we decide what is the level of significance that we want to perform this test at. Most of the time in the problems that you'll approach, that's kind of just given to you. But remember, the lower we set that number, if we take it, say, from 10% to 5% to 1%, we're actually, the lower that goes, we're raising the bar on the amount of evidence that is needed to reject the null. So the lower the significance level, the more difficult it is for us to get a p-value that will be less than that significance level. Next thing, now we just need to gather some evidence. And the evidence is going to come from our random sample that we take. So we take a random sample and we find the mean, or we find the percentage of that, depending on what type of parameter we're measuring. And we convert that either into a T or a Z test statistic. The test statistic tells us the distance from normal, or the distance our sample result is from the center, from normal. The normal represents what the null is claiming. So the further I am away from that center, the more evidence I'm gathering against the null, which states that this is where the center is. After we've calculated that, what we're actually going to use is not the distance that our value is from the center. That's a critical value approach, which we're not going to be using in this part. Instead, we're going to find the probability value for that test statistic by usually going in the same direction as my alternative hypothesis. So if my test statistic falls on the right, and as I suspected, the alternative area is to the right, then we're going to find that area, and that will be my probability. Again, our goal is to get a p-value less than our significance level. So typically, our p-value is found near the edges of the curve. In other words, the tails. But we really have to look to the alternative to see what direction we're going to find the area of. Once we've compared the significance level to our p-value, we draw a conclusion based on the above comparison, and we use that template that's been provided for you for this. We either reject or fail to reject the null, and then we state whether the evidence supports or does not support the alternative. Your conclusions must be stated in those terms. So let's take a look at a couple examples. We'll go through this together. So Wikipedia, a free online encyclopedia, reports that in 2006, the average American woman is 25 years of age at her first marriage. A researcher claims that for women in California, this estimate is too low. Surveying 213 newlywed women in California gave a mean of 25.4 years with a population standard deviation of 2.3 years. Using a 95% confidence level, determine if the data supports the researcher's claim. So first, let's take a look at our null and alternative hypotheses. Here, when we talk about the number that's in dispute, it's the average age of women at her first marriage. The dispute is really women in general versus women in California. The researcher claims that Californian women, it's different. But the disputed number here is the mean. So we are dealing with a mean, a population mean. So for our null hypothesis, we would say mean equal to 25. Then we have to say, what is the researcher claiming, or what are we believing is the change here? And he or she says that it is too low. So here we would state that they believe it's more than 25. If they think 25 is too low, they obviously believe that the mean has changed, so it's above 25. Notice that, again, we're two alternatives for the same number, 25. Your null alternative should always have the same number. All right. Now we want to gather evidence, right? And so the evidence is gathered. We take a sample. We survey 213 newlywed women. And so that's my N. And it seems as though there might be some legitimacy to this claim, right? Our sample result is 25.4 years. And then we're told there is a population standard deviation of 2.3 years. Now, this tells me that since it's a population, this is the key word here, this is a sigma, and therefore, this is a symbol is used for therefore, we're going to be using the z-curve. So this curve that we're looking at that we can use is z because we were given the population standard deviation. We're going to test this at a 95% level of confidence, and we're assuming the null to be true, right? So at the center here of the universe is 25. This is what the null is stating. And so we're going to say, all right, let's look at it from that perspective. If it is 25, what would be the chance that I would get 25.4 with a sample size of 213, assuming that 25 really is the center of the population? The probability of that will be found to the right of this value. Now, I actually don't know off the top of my head. In reality, I don't know how extreme 25.4 is. It might be extreme for a large sample, but it may not be extreme for a smaller sample or what have you. Like the sample size really can affect that. And also, of course, the standard deviation. So for us to test that, we need to look at the z equivalent of this number. These are my mean values. Now let's look at what it is as a z. And again, we know it's a z because we had the standard deviation of the population given to me. 25.4 minus 25. And we're going to divide that by the standard deviation, 2.3 over the square root of my sample size, which was 213. If you're doing this, make sure you put parentheses around the top. And also, even more importantly, around this bottom division. You can get away without putting it in, without using parentheses on top if you hit enter after your subtraction and then hit divided by, but then you need to use parentheses on the bottom. Put that into your calculator, and you should get 2.538. So, I'm probably even a little bit further than I've drawn here, but let's go ahead and put this in there. 2.538. So that is 2.5, more than 2.5, slightly more than 2.5 standard deviations to the right. That tells me it is kind of far, right, into the tail. We know that most data, 95% of it is within 2, so this is beyond 2. Now, how far it is and whether it's significant enough for us depends on what the probability is of this occurrence. The p-value tells us the probability. This is a z-curve. Sorry, I'm losing my thought process there, playing around with this. This is a z-curve, and so I need to use normal CDF in my calculation of the p-value. We're going to go 2.538. Notice I take these to 3 decimal places. That's usually a good amount. Comma 1,000, comma 0, comma 1. And this will give me my p-value, which is 0.0056. If we round it to 4 decimal places, generally, as you guys know, probability we like to take to 4 decimal places. So the p-value that we found here using normal CDF, 0.0056. We used normal CDF because we determined this was a z-curve. Otherwise, we would have used TCDF on our calculators. And this is less than my significance level, which was 0.05. Whenever our p-value is less than our significance level, we have successfully challenged and are rejecting the null. So here's how we would write our conclusion. We reject the null. That's our first part. Whenever we talk about rejecting, it's always in relationship to the null hypothesis, not to the alternative. We never talk about rejecting or failing to reject the alternative. And then we do say, the second part, we want to talk about the alternative and whether the evidence supports it or not. According to our template, we would say there is sufficient evidence to suggest that, and then we are going to put the alternative hypothesis into words. The average age of women is greater than 25 . I should say women of California. Right, that's a little more specific here. Is greater than 25 at their first marriage. So remember that when we reject the null, we're always saying that there's sufficient evidence to support the alternative, right? And then you want to put the alternative into words that are understandable, even to somebody who is not taking statistics or is not a statistics person. It should be very clear what we are concluding in our wording. Okay, let's look at another example. Local high school board has been advertising that 65% of voters favor a tax increase to pay for a new school. A local politician believes that less than 65% of his constituents favor the tax increase. To test his claim, he asked 50 of his constituents, and 27 said they favored the increase. If the politician wishes to be 95% confident in his conclusion, does the information support his claim? So again, what is the disputed number here? The disputed number is 65%. This is the claim about the population, that 65% of voters favor a tax increase. This person disagrees with that. And so 65 is the number. He believes that less than 65% of his constituents favor the tax increase. So the number that we're in dispute here is a percentage of a population, right? If we were to collect it, it would be based on categorical data, non-numerical data, yeses and nos, basically, do you support the measure? And then the only thing we can really do with that is turn it into a percentage. So we have a P, a proportion that's in dispute. P equal to 0.65 is the null hypothesis. The alternative, the researcher, the politician believes it's less than that, so we're going to go less than 0.65. Notice that with proportions, we have a different symbol here. And it's important to, at the outset, have that very clear to yourself, because then if you've created your note card, you know that automatically you want to use those formulas, right, that are for that. So we have the dispute is at 65. We get something less than that, and we test that. So P hat yields us 27 out of 50, which is 54%, so 0.54. That's less than 0.65, but the question is it significantly less? The only way we can tell is because it varies. Sometimes this may be enough, sometimes this may not be enough. It really depends on the size of the sample and the measurement that we're using. So because we're doing a proportion, remember that with proportions, as long as my sample size is big enough, then we can use, and for our purposes, we can use Z, and for our purposes, we always will. So with proportions, you can just be confident that we're going to use Z. So we're going to go 0.54, the result of my sample. It's always the result of your sample minus the null, right? The assumed value of the population. And then on the bottom, we're going to divide by this square root formula that tells us the average spread. So we're dividing it by the deviation, the average deviation. Remember that you want to use here 0.65 times its complement, 0.35, divided by the size of the sample, which was 50. And so just keep in mind that the population number is what goes down here. In a margin of error formula, since we don't know the population number, we actually use the sample p hat value to do that. But here, since we are assuming to know the population parameter, p, that's what we use in our formula. It's kind of a superior number, if that makes sense. Anyway, punching these in, we get our z value of negative 1.631. Now, just as some advice as you're watching these videos, and if you're using a blank one, which are available online as well, you can kind of fill this out as we go and test yourself as we go as well. And so if you pause the video, calculate these. It's really important to feel comfortable and confident punching these things into your calculator, because as you know, there's some pitfalls. Number one, if you don't put parentheses up here, you're going to run into problems. And making sure when you open a parenthesis with your square root that you close it at the proper place. For some of your calculators, if they're more updated, the little bar across the top of the square root there, the radical symbol, will continue to move, which shows you what is actually underneath the square root. But for a lot of older ones, you have to show what's under the square root with your parentheses. So there's lots of ways that you want to practice with this with your particular calculators, so you're getting the same answer as I am. And that's going to give you more confidence as you approach these. So what I see with this is that, again, this is my proportion values, and then underneath that I'm going to put my z values. 54 is a little more than 1.5 standard deviations away from the mean. And the area to its left is going to be my p-value. We know it's the area to the left because the alternative hypothesis is pointing to the left. What that tells us is that is where the extreme area of the curve is, and the definition of p-value is the probability we would get this result under the conditions of the null or something more extreme. And so we go in the direction of the alternative hypothesis in determining where that extreme area is. This is a z-curve, so I'm going to use normal CDF, negative 1,000 lower boundary up to negative 1.631, comma 0, comma 1, to get the probability, which is the area in that curve, which is 0.0514. So my probability value for this test, 0.0514, we're going to compare to my significance level. Now, we were told we wanted to be 95% confident. That tells me my significance level, alpha, is 0.05. The confidence level is always the complement of the significance level. And in this case, my p-value is slightly greater than my significance level. This tells me that though my evidence was 11% different, that this isn't enough evidence for me to conclude that it's different from 65. Most likely because the sample here is pretty small, 50. So with a larger sample, this might have been enough. In this case, was not enough. So my conclusion here would be to fail to reject the null hypothesis. And that is the wording we use. We never say fail to accept or accept. We never say that. We say either reject or fail to reject. We continue now and say, does the evidence support or not support the alternative? If we fail to reject, we say there is insufficient evidence to suggest that less than 65% of his constituents favor the tax increase. Right? Stick to the script. Stick, because when I'm grading these, I'm looking at, are they sticking to the script? Not if they're using the exact right words, but there is some keywords like reject or fail to reject. You don't have to use exacting, but the meaning needs to be the same. We say whether or not the evidence supports or does not support the alternative. In this case, we're saying there's insufficient evidence to support the alternative, and then I'm just stating what the alternative is saying, and then I failed to reject the null. We always reject or fail to reject the null, say there's sufficient or insufficient evidence to support the alternative. Okay, we're moving pretty good here. Let's take a look at another one. And again, I encourage you to, rather than just passively watch me do this, which it's a lot easier when you're watching somebody else do it and kind of talk you through it. When you sit down to do it yourself, it takes on a whole different level of difficulty. So the best thing you can do for yourself is to do it along with me. And then you're already getting some practice in the thought process and in putting these things into your calculator. Okay, Sarah, a university junior, chose to live on the honors floor of her dorm because she was told that the girls on that floor would be quiet and studious. In fact, Sarah was told that students on the floor study on average 11 hours per week. After living on the honors floor for a few months, Sarah is convinced that the students around her study less than 11 hours per week. To test her claim, Sarah polls 10 girls on the floor. Test Sarah's claim, given the results below at a 10% level of significance. Okay, so the number under question here is the number of hours, the average hours spent per week. So this is a mean, right? We're not talking about a percentage. And 11's the disputed number. So I know mu is equal to 11. And then with the alternative, we just have to say what is in the mind of the researcher. And in this case, she was told that she believes that they study less than 11 hours per week. So we're going to use a less than symbol. Right? So the dispute here is the population mean. Is it 11 or is it something different than that? or less than that. So what we have here is we have the level of significance here. This is my alpha. So this is what we're going to compare the p-value to. We know that 10 is the n, but that's all we were given here. But we were given the sample data. So this is what we want to put into our calculators. The two things that I need in order to move to the next step here is to figure out what's the average, right? What's the study average? And then because I'm not given a standard deviation here, I'm also going to use S as my estimation of the population number because we're not given the standard deviation of the population. The only way I can derive that, which we need for our formulas, is to use the sample data. So we're going to say, the sample came from the population, so we're going to look at its average, and we're going to look at its average spread, right, average deviation. And we're going to use that as an estimate of how we think the population might be spread as well. Because we always assume that a random sample should produce something close to the population values. Putting these into our calculators then, we get x bar is equal to 9.5, and my S value is 2.991. I try to take, especially for standard deviation, take it out a couple of, here I just took it out to 3. 2 or 3 is usually sufficient. Obviously the more you take it out, the less you're rounding, and so that makes it a little more accurate. For your purposes, we're just trying to get it close enough to and the accuracy level that the computer will accept your answer. So 11 was the assumed center, right? And we got 9.5. This is when we're discussing it in terms of average, right? Average hours per week studied. Now, what is the test statistic? That's the question. And is it a T or a Z? Because we are using S, because we were not given sigma, this signals to me that we need to use T. S is an estimate, and T morphs with the size of your sample. The curve itself gets more and more accurate. The larger your sample is, more and more close to replicating the Z curve, but is better used on smaller samples, but also just samples where we don't know the standard deviation of the population. So we are going to use T, and of course T, just like Z, has 0, where the center of the curve is. And then we just need to figure out what's this. We know it's going to be something negative because it's to the left of 0, but we definitely know this is a T. And this is important too, establishing this. It's one of the key things. If you're having trouble getting you're getting the test statistic right, so you're doing that calculation right, but then your p-value is off all the time, the first thing you need to suspect is you're possibly using normal CDF where you should be using TCDF, or vice versa. That should be the very first thing you check. Okay, so my sample result was exactly 9.5. We're going to subtract 11 from that, and then we divide this by 2.911, or 991, over the square root of 10. Remember that both the top and the bottom need to go into parentheses, and we can calculate our T test statistic. You should get, of course, negative, because it's on the left. If you got positive, that tells you you're putting your numbers in the wrong order on top. So negative 1.586. So the T equivalent of 9.5 is negative 1.586. This is so I'm I'm a little more than 1.5 standard deviations away from 0 to the left of center. Here's my area. This is a left-tailed test, so that's where I'm going to find my p-value. And in this case, this is a t-curve, and so we need to use t-CDF, not normal CDF, right? Invert t, t-CDF, that's what we use with t-curves. Normal CDF and invert norm, that's what we use for z-curves. negative 1,000, all the way up to negative 1.586 with 9 degrees of freedom. And this is my p-value for this test. Plugging that in, you should get 0.0736. This is the area to the left of my test statistics, it's my p-value, and so that is my probability value, 0.0736. What this is saying is that under the conditions of the null, there is a 7.36% probability that we would see a result like this if the true mean truly was 11, right? If 11 hours was really the true population mean, there's a 7% chance of seeing the result that I saw with my random sample. Now, 7% is really low, right? If I say there's only a 7% chance of rain, you're probably going to leave your raincoat at home if you even have a raincoat. But because it's very unlikely, right? 7%, we don't normally even blink an eye at that. But in the case where we're giving the null a lot of precedence, which is hypothesis testing, we give the null a lot of precedence. We have to have a low number there, and it has to be low enough that this would happen in a very rare, we would rarely make the wrong decision here. And, in this case, our significance level was 10%. So we're saying anything less than 10%, less than or equal to 10%, is extreme enough and is enough evidence for us to reject the null. And in this case, it is, because we had 10%. And so we can write our conclusion. Say there is, we need to start off with the first thing, which is to reject the null. There is sufficient evidence. So reject, sufficient. There's sufficient evidence to suggest the girls study less than 11 hours per week. All right, that's what we decided. Now, for many other significance levels, for example, the one below 10 that we would usually use is 5%. This would fail to reject at the 5% level of significance. So our level of significance is really important. Now, is a level of significance always used? No. The lower your p-value, that enough is evidence against the null. And most people who are familiar with testing, scientists, statisticians, etc., understand that if you say I had a p-value of 7.3%, but that's kind of on the borderline, right? Well, okay. Evidence is there, but it's not really beyond reasonable doubt low, right? If we had 0.00736, that would be really strong evidence here. So just so you're aware that it is what, for our purposes, we use the significance level to compare it to, but in reality, it's a sliding scale, and it's very subjective. We are picking, and in a case like this where there's not a lot of consequences to us being wrong, right? Nobody's going to die because of it. She's just trying to see how it grows on her for study. She can probably pick that 10% and be okay with it. But keep in mind, the p-value is a probability value, and it's a probability of seeing what we're seeing. It's a probability of the evidence we've seen under the conditions of the null. And so the smaller our p-value is, the more likely we're going to reject the null. We're going to do one more here. A recent study showed that the average number of children in Europe is 1.48. A global watch group claims that German women have an average fertility rate which is different from the rest of Europe. To test their claim, they surveyed 128 German women and found that they have an average fertility rate of 1.38 children. We assume the standard deviation of the population is available from previous studies and is 0.84. Does this data support the claim made by the Global Watch Group at a 90% level of confidence? Okay, a recent study showed the average number of children. The Global Watch Group claims that for German women, their fertility rate is different. So let's talk about the number we're challenging. The number we're challenging is at 1.48. This is an average, right? So we would say mu equals 1.48. And then the alternative, well, they're not really committal, is it? The word they're using here is different from the rest of Europe. Different doesn't really give us a direction. And so this is, when we see non-committal words like that, we know that we're just going to do a two-tailed test. We're maybe not sure, so we're just saying, not equal to. Because remember, we're generally kind of putting forth the hypotheses before we actually collect any evidence. And so if we were simply, because our sample result, which is the 1.38 here, that was my X bar. And of course, 1.38 is less than the 1.48. So we might mistakenly say, 1.39. We might mistakenly say that, it must be a left-tailed test. But if we were to use the sample result to determine our direction, we would never have a two-tailed test. So just keep that in mind. Okay, we're also told that the population standard deviation is available from previous studies and is 0.84. That makes 0.84 a sigma. And if we have sigma, then we can use z. So we're going to go back to the z curve for this problem. And in this case, 1.48 is my assumed population center. And we got something less than that. I'm just going to put it off to the left. I don't know how far it is until I've actually calculated the test statistic. And that's what we want to find. And we can expect, looking here, that it is going to be a negative. So 1.39 minus 1.48 divided by the standard deviation, which is 0.84, over the square root of my sample size, which was 128. In general, remember that a larger sample, for a larger sample, we need less, or we can expect to have less deviation. So even a small deviation can actually produce a fairly large z. Let's go ahead and calculate this out. Remember to put your top part in parentheses and your bottom part in parentheses as well. We should get negative 1.212. So negative 1.212 is the number of deviations. I'm just a little more than one standard deviation to the left. Now, because this is a not equal to in my alternative hypothesis, when I go to find the p-value, I need to use not only the area to the left of negative 1.212, but also the area to the right of positive 1.212. Both of these together give us the p-value or the probability value. So there's a couple ways to write this out. We can go 1 minus and then go from the negative to the positive. So in other words, find the area in between, subtract that from 1. That'll give me the total area in both. Or I can just find 1 and then double it. We're using normal CDF. So if I go on the left here, that's negative 1,000 up to negative 1.212, comma 0, comma 1, to give me my p-value. Well, actually, it'll just give me the area for this point. And we end up getting 0.11275. Actually, 276 if I round it. But let's go ahead and just double that, because I would also need to include the area that's over here. So the total p-value is 0.2255. And that should include this area along with that. So 2255, which is greater in this case than my significance level, which, since we're at a 90% level of confidence, my significance level is 10%. This is greater than that, and so our conclusion is to fail to reject the null hypothesis. There is insufficient evidence to suggest the fertility rate for German women is different than 1.48. And there we have our confidence intervals. There we have our hypothesis tests. Remember that you can go back, rewatch these, follow along, and just keep working on these. Eventually, these steps kind of become second nature to you. But always be reading and thinking about each step. What is the number that's being challenged? Am I using a Z or a T? Using the correct functions on your calculator to find those p-values. And remember that in general, what we're looking for in order to reject the null, which is our goal as a researcher, is to get a p-value that's less than my significance level.